put some stuff up about that again. Direct delta. And the idea was, and we had a bunch of realizations of it, the idea was that you've got integral delta of x dx over the entire real axis. But this delta function is equal to infinity at 0 and 0 everywhere else. It's the limit of some kind of spike function. So that equals 1. So very roughly speaking, it's equal to infinity at x equals 0, 0 at x not equal to 0. And then if you have an integral with this form, f of x delta, say, x minus a, or I'll just write x naught, x minus x naught, then this spike occurs at x of 0, and out pops f of x of 0. And then what we found was, well, this is not a function per se, but it's defined by this operation here. Then we had a delta sequence, and then you actually have a function, delta sub n of x. So these are actual functions with integral delta sub n of x dx is equal to 1. So then you have actual functions, and in their limit they have the spike form more and more. Okay? So you'll find those homework problems pretty interesting, actually. Just for the record, I'll put a couple of these up here. The one we did yesterday in the recitation was actually pretty good. This one here, because it takes us back to our contour integration. So this example we had, and this is one of the homework problems to show that it's normalized. Delta n of x equals n divided by pi, and then 1 plus n squared x squared. Okay. So you can see when x is equal to 0, in the limit as n goes to infinity, this thing diverges. Okay. And the shape of this thing becomes narrower and narrower the larger n is. So the key to solving this one is just to factor it a little bit differently. So you've got the n over pi. You pull out a 1 over n squared, and then you have x squared plus 1 over n, the quantity squared here. And I'm about to do this one again because it's a good example. You know, remember we had x squared plus 1, and we did x plus I at x minus I. And we can do exactly the same thing here. And then we can do a contour integration. You know, it'll have these two poles, except this time they're I over n. Okay. But it doesn't matter, as long as you have a finite n, you do your good old integral of this kind of type, and then the residue theorem, 2 pi I, this thing, and the integral actually turns out to be equal to 1 minus infinity to infinity. So this is the perfect example, and it makes use of these. But I had a half dozen other examples, or several other examples, and I think when you work those, you'll see they're interesting as well. Okay. So, and we motivated the delta function by putting it into our solution of the heat equation. Okay, so that's also working through the heat equation solution that I put on the board. There's a couple of unfinished steps that are also pretty interesting. So yeah, you guys will enjoy that. And I think what we're going to do is just a couple of delta function homework as well. So here we have properties of the delta function. One of them, delta of AX equals 1 over A delta of X. And I'll just put, you can figure out, I'll just say 1 over A delta of X, A greater than 0. So A is a constant, and this is the basic substitution. So you can easily prove this. But this one comes into this, change of variables, so that one happens all the time. So you definitely have to know this one. And the other one is delta of G of X. So suppose you have, a delta function, but inside there you have another function, G of X. Then you're going to have to take into account that this G of X may have more than one zero. It could vanish in more than one place, and then you'd have a whole bunch of these. So what you'll find here is you get the sum of delta of X minus A sub I. Here, I'll just write this down. G prime of A sub I magnitude. And these are the zeros. So where G of A sub I equals 0, we get a collection of those. And of course, G prime of A sub I is not equal to 0. I was going to put these on the homework, and that'll complete the set, probably. So let me see, we got some tips here. Actually, that's a third one, which is good too. Let me go ahead and erase this. So the third one is, what does it mean to take the derivative of the delta function? So f of x delta prime x minus x0 dx. And that is going to be equal to minus f prime of x0. So homework is to do 1, 2, and 3 here. And let's see, because we can actually just do these. Yeah, this is going to be a very basic substitution, so this won't give you no problem at all. This one here we need a tip on that. Let's see. This one here. So this third one, what you do is you use delta sub n of x minus x naught, because remember the delta sub n is a continuous function on the sequence. So use the delta sub n, then do integration by parts. And then take your limit, and you'll see it comes right out. And so basically what that does is that defines your delta prime as an operation. Okay. So yeah, if you put in delta, just replace this with delta sub n of x minus x naught prime, and then treat it like a continuous function that it is. Then you can do the integration by parts. And then when you take the limit, you'll see that the only thing that's left is minus f prime of x zero. So yeah, these come into play in applications all the time, especially this one. This one here, this one you have multiple, well, you have multiple zeros, but the way this one comes into play most often is just one of these, right? It'll be delta x minus x of I divided by g prime. So these are pretty common in applications. So yeah, you prove those, look at this one first, and then you'll see where this one's coming from. Okay. You may expand. Yeah, I'll give tips, why not? Okay, this one, integrated by parts. This one here, about every zero of g, you do a quick expansion. Right? And you're looking at it, expand it out there, that's where that g line is going to come from. Okay. G of x approximately g of base of I plus g prime of base of I x minus x of I, right? So close to every zero, you have a little Taylor expansion. This one by definition is 0, and then this reduces to column number 1. So you just take these in order, and you'll see they're pretty good. That, I think, is going to be our chapter. The rest, that completes our chapter on delta function. There's more here, but we can't do everything. Okay. And who's going to be here after class anyway? Yeah. And that's right, you can show up too. Anything prepared so far? We had some good problems. We did some good ones yesterday. So yeah. Good, so that ends our section on the delta function. Who remembers the multivariable Taylor expansion? Some people should remember it.
I don't think I ever learned that.
Okay, good, we'll take our time on it. So, I'm trying to follow a thread. And the thread is that we started with Taylor expansion at the very beginning of the semester. We started with the definition of the derivative. And so we're just going to extend that discussion into multivariable calculus. We found we needed multivariable calculus when we started talking about the heat equation as a nice example. And so we also spent a little time already talking about div grad curl and the integral theorems. So now we're just going to do the multivariable Taylor expansion. And then you'll see how much you remember. Okay, that's our topic. And first we go back to n equals 1. So recall for n equals 1, what would our Taylor expansion look like? We said we've got f of x equals f of x 0, f prime of x 0, x minus x 0, plus a half, x minus x 0 squared, and then higher terms. Now in the multivariable Taylor expansion, we can also go higher terms, but we're going to stop at the second derivative. Okay. And for n n equals 1 also, you know, this just was our basic analysis of functions. Okay, so that when you first learned calculus, you learned the meaning of the first and second derivatives. And this is really just analyzing the curve. Say we had a x0 right here. Then the first derivative was 0. Second derivative was positive. And in fact, this is f of x0 and the meaning of this f double prime x minus x0 squared was that it was the parabola that just nests in there. Okay. And so for purposes of approximation, if you were close to x of 0, you had a very good approximation. Then, for example, if you were interested in linearizing a function, say you were interested in this function out here, we'll call it x of 1. You're interested in out here and you just, you know, want to put a ruler up against it. Then up here we would have had f of x equals f of x1 plus f prime of x1, x minus x naught, and that would have been the equation of this straight line here. Point slope formula. Okay. So this is going to generalize to functions of n variables. And the conceptual framework is exactly the same. First derivative linearizes, second derivative finds a local curvature. Okay. Remember that we showed that the second derivative at x naught here at a local minimum is actually the curvature of that radius, you know, gives us the 1 over the radius curvature. Good, so what about n variables? Then we have our work cut out for us, but it's actually going to follow this. Oh, I should say one more thing for, in the multivariable, we're going to make use of the chain rule quite a bit. Okay, so that's going to come up repeatedly. But for n greater than 1, you know, we have, I'm just going to write examples. You have r equals x1, x2, x3. And then we could have, for example, f of r is equal to r. And that is the square root of x1 squared plus x2 squared plus x3 squared. You can say x, y, and z as well, but 1, 2, and 3 because we're going to generalize. Or f of r is equal to 1 over r equals 1 over the same thing here. So if we're comfortable with that, we can also do f of x equals 1 over magnitude x, 1 over x1 squared plus x2 squared, all the way out to x of n squared to the 1/2 power. Have you guys run into those kind of generalizations before? N variables, x1 to xn. Anybody know? Yes, no, maybe? Yes. Yeah. Okay. So yeah, you see I switched from R just to vector x, and vector x means it has n components. We're familiar with the 3. This generalizes to n. And n can be really large. In theoretical calculations, it could be the number of particles in the gas in this room. Okay, so this is the number n. Good. So how are we going to do Taylor expansions in this form? Okay, let's go ahead and erase this. this of f of x, x1, all the way out to x of n. And we'll use the magnitude of x as I just described right there. It's 1 squared all the way to x squared, the 1/2 power. But how do we expand something like this? Let me show you. Suppose we have a point in space x0 and a point in space x. Then what is this little vector I drew up there? This little difference vector, this is my x minus x0. And this could be the point of interest, you know, the origin could be very far away. Could be the point of interest, and then this x minus x of 0 could actually be a small quantity. That's the way we're going to look at it. So this is the small quantity, this is the point. We'll label it here, right? This is the x0, that's that point right there. And this is the origin somewhere. Okay. So here's the way we do this. We're going to let g of t is going to be a parameter, be equal to f of x0 plus t times x minus x0. It's actually an amazing construction. So what is this g of t now? When t is equal to 0, I'm just at f of x0. I'll use a different color. I'm going to redraw this. I'm going to redraw this one. Slight improvement. Okay. So this is my x0 vector. This is my x vector. This here is x minus x0. So when t is equal to 0, I'm just right here. And as I let t grow, when t equals to 1, I'm over at x. T equals minus 1, I'd be somewhere over here to the left. So x minus x0 is just an arrow, and this red dotted line is what g of t covers. So this is a parameterization of this red dotted line. And the strategy is we're going to do a Taylor expansion of g because we know how to do that. So we're going to expand g of t so that what do we get? So that g of t equals g of 0 plus g prime of 0 times t plus 1/2 g double prime of 0 times t squared. That's as far as we're going to go. We could go more. And then g of t equals 1 is equal to you go back up to here is equal to f of x. It's amazing little construction. So now we, right, because if I go up to here, t equals 1, x0 plus 1 times x minus 1 times x0. So I'm left with g of t equals 1 is f of x, but what I'll have done is expanded it out in an interesting sum. So let's go ahead and give that a try. Here's where we have to unleash the chain rule. So once we do the first one, we'll see what's going on. So we need g, we already know we have, I'll go ahead and put this out. We have g of 0 equals f of x0. about G prime of t? Now, G prime of t is equal to d over dt f. I'm gonna write everything out carefully. X 0, 1 plus t x1 minus x0, 1. This is where the bookkeeping plays a role. Okay, because this here has n slots, right? N variables. So this was a vector, but now it has n variables, so each one is of this form. x02 plus t x2 minus x02, comma, plus all the way out to n. I can keep writing. So now we have to remember the chain rule. The chain rule is to take partial f with respect to x sub k x0 plus t x minus x0. Writing out the compact way again. So we have to do the kth slot, 1, 2, 3, all the way to n. And so the rule is just, and then times the inner derivative, but the inner derivative with respect to t is just, right, the inner derivative with respect to t is just as x1 minus x01 or xk minus x0k. So this would be the chain rule if all we had was this one variable. And the rule is just to add them all up in the sum. So that's k equals 1 to n. And when we evaluate it at t equals 0, we're just going to set this t equals 0. Okay. So what I have here behind or on this side of the sigma is just an ordinary chain rule. Ordinary chain rule, and in fact that's going to give us, it's going to give us this one because we're going to evaluate it at t equals 0. Okay, but we have one more step to do. So this is g prime of t. We'll hold on to this and we'll evaluate it. But like I said, it's a lot of bookkeeping. Right here in the argument, I've got the whole vector thing. Here I did the one at a time. So what about g double prime of t? For g double prime of t, we have to treat this entire thing as one of these. So for the second derivative, we're going to add a summation j equals 1 to n, because we're going to do the same thing along the whole string of variables. And we already have this one in here. K equals 1 to n. We're again going to take the first derivative, but we already have derivatives here. So it's going to be dxj, I'm going to write this out, df dxk x naught plus t x minus x naught. And I also have this xk minus x0k. So we take the dxj of this thing, just like we did the first one here, and now we bring out an xj minus x0j. And so we have a double sum. And once you see how this game is played, you can can see that the third derivative would be a triple sum and the fourth derivative would be a quadruple sum. So you can actually just write them down or have the machine write it down. But we're just going to the second derivative, which gives a really classic and important expression. Okay. So actually we've done all the work there. It was all just chain rule. So put here in red, chain rule with exclamation. Chain rule. And now we can just start to analyze these things. So I already mentioned t equals 0 here, it's df dx k of x 0. T equals 0 in here, it's d squared f dx j dx k. So we've got room over here, I'm going to write these down. So we're going to have g of t equals g of 0 plus g prime of 0 t plus 1/2 g double prime of 0 t squared. So these derivatives are evaluated at 0, and then the t's are evaluated at 1. So we're going to end up with f of x equals f of x 0. That was the g there, right? G of 0. The g prime of 0 is this thing here, and times t equals. So right here, evaluate at t equals 1 to obtain. Here we go. Plus sum over. Here, I'm gonna write this. Need it. Okay, so we end up with f of x equals f of x 0. Now we're doing that first sum, so we have sum over df dxk of x 0, and then xk minus x 0k. So what's the next one going to look like? The next one, it's got the 1/2, the g double prime of 0, you're going to put a t equals 0 in here, and you're going to see enough of these double sums in the future, so you'll get used to them. jk d squared f dxj dxk at x 0. And then we have the xj minus x0j. I'll write that one first. xj minus x0j of xk minus x0k. Summations 1 to n. And when the dust settles, you could actually just start writing out the higher ones. What would the third derivative be if we wanted it? Anybody see this process going on? So in other words, what would the next term be here? It would be 1 over 3 factorial, just for fun. It'd be 1 over 3 factorial, then what? Triple sum. What kind of subscripts do we want to have there? IJK sounds good. Nice order. IJK. What would we have in the derivatives there? This is like an inductive thing. We saw 2 of them, the third one. See, we had first derivatives here, we have second derivatives here.
I don't know about the denominator.
How about the numerator? time just adds another, and you know, we would just keep doing what we did here, so it's actually no mystery. And then t equals 0 would be evaluated at x0, and then we would have this thing, xi minus x0i, xj minus x0j, xk minus x0k. So yeah, you could just keep writing them out. But we only want to go to the second derivative, and there's important reasons for that. Second derivative is a quadratic form. It comes up all over the place in physics. The third one, you know, this is just for culture. But you can see how it would be done. Now, if n is equal to 10, you know, you've got a vector with 10 components, you've got 10 times 10 here, you have 1,000 there, so you don't want to go there, right? But up until the second, writing down this third one is just in order to recognize the process that we followed to get this. It's actually very straightforward. What we needed was a multivariable chain rule, okay? Which, by the way, I haven't really given you a proof, but we'll get the proof later on in the semester. Okay, good. So now this thing, I'm going to go ahead and erase this one. You guys have it for the record, right? You can do 4 or 5, whatever. But let's directly underneath this go back to our one variable n equals 1 case, so that you can really see what's going on. So for n equals 1, we have f of x equals f of x0. Here I'll even write df dx of x0, x minus x0, 1/2 dx squared, x minus x0 squared. So what's the difference between these two? Conceptually, they're exactly the same thing. This is a single variable version, and this is included in this definition, n equals 1. So, there's an important lesson here. When things start getting complicated in math and physics, and they will, there's really complicated formulas, you want to hold the actual concept in your mind, what's actually going on here. So you've got all these indices and stuff, and it looks kind of bad. It's really, you know, a constant, a linear term, a quadratic term, and so forth. Okay? You have to see things that way, so you don't get, you know, inundated with subscripts. So just as with our analysis a minute ago, in your mind's eye, for this expression up here, you're seeing this down here. Okay? In fact, it's going to have the same criterion for a local minimum. For a local minimum up here, we're going to want all of these n derivatives to vanish, okay, or a local maximum for a critical point. Okay, so what's another way to look at this? Yeah, so we actually have to write some of these things out and get a feel for them as well. Okay. So we need some examples. Well, my first example is this thing here. Okay. You guys should really feel comfortable with this. Right. Taylor expansion, constant, straight line, parabola, and so forth. So do we see that up here? You may have seen this before, f of r naught plus gradient f of r dot delta r. So I could write delta f is equal to gradient of f dot delta r. You guys familiar with that kind of expression? Potentials, forces, things like that. So familiar with that? Are you guys seeing this kind of thing before? Yeah. So written out, right, delta F, this would just be F of R minus F of R naught, right? Change in F, and you know, delta F equals F prime delta X in one variable. Okay? So in three variables, it would be the gradient dotted into delta R. You know, you could have called this df dx delta x plus df dy delta y plus df dz delta z. Okay. So this, hopefully this looks familiar too, okay? Because this is exactly what we have here in the first term, except with n variables. Each of these xk minus x0k, that's just a little delta x. And there's a derivative, and this df dxk is a gradient f in n variables. Okay? So this dot product here, I just wrote out a dot product, is what we have right here. Okay? So that covers the linear example. So I'll just write here to complete this thought. In this expression star, we have, you know, f of x minus f of x naught. Just subtracting that over equals, you know, that sum df dxk xk minus x0k. I'm just going to take it to the linear term, and that is the same as a gradient of f evaluated at x dotted into a delta x, because those are just the individual delta x's. So that's what that's the meaning of this here so far. Just a linear approximation with more subscripts to kind of, you know, to irritate you, but this is basically what's going on. Now the second one is a little more complicated, but not too much. So if we can just do something similar for the second, and I can't, in fact, so how about this? This make sense? This one right here, just the, you know, generalization. I'm gonna erase this here, leave the big formula out. Now for the quadratic term, there's more going on. So now we're looking at the quadratic term. But let's make a shorthand. So for the quadratic form, quadratic term, let f sub jk equals e squared f dxj xk. That's a nice shorthand. In fact, they're evaluated at x0, so they're constants. So these are all constants, and we're going to let delta x j equal xj0. I'm sorry, xj minus xj0. So that's that small quantity. Then our double sum looks like this. So we've got a half double sum jk f sub jk delta xj delta xk. So that simplifies that a fair amount, right? And these f's are constants because very important to Taylor expansion. You're evaluating at a point, so they're constants. And we just got a shorthand for these little small differences. And who remembers matrix multiplication? So this fjk, note that fjk is matrix. You can say it's F11 all the way to F1n, Fn1 to Fnn. We actually have a section coming up on linear algebra where we'll be a little more systematic with the matrices and stuff, but this is where they come up. This just came up from the chain rule. We have to start somewhere, right? Oh yeah, this is a matrix. And so this double sum is some kind of matrix multiplication going on. Okay. Matrix multiplication twice. So we would have, for example, if we did f j k delta x k, k equals 1 to n. This will be a row times a column. A row of the matrix F times a column, delta x k is a column. Okay. And so row times a column, and then the second sum, the sum over the j's, is actually like an inner product between the vector. This is now a vector. This is a vector. This is a vector jth component, and then the second summation really does what the first one does here. So yeah, these kind of double sums are very common in physics, called a quadratic form. Square matrix, quadratic form, and critical points we have to be able to talk about here as well. Okay. So we're always going to leave this big formula up on the board. We'll just work with the small square right here. Let's write out a little more of these. Okay, so this is general. Let's look up a 2 by 2 matrix. Okay, 2 by 2 problem. So 2 variables. Okay, so I'm going to go ahead and erase this. Let's call this example. Example, f of x equals f of x1 and x2. F of x1 and x2. So 2 variables. So now we have f of x1, x2 equals f of x1, 0, x2, 0. Takes care of the first one. And then we're going to have df dx1, I'll just short off right x0, times x1 minus x1, 0, plus df dx2, x2 minus x2, 0. So that takes care of these linear terms. And you know, we could, at this stage, we can also have x and y. Make it easier to write as well. We have x and y. What about the third ones? And here's where you're going to see the bookkeeping come into play. Yeah, here it goes. So d squared f dx1 dx1 x1 minus x1, 0. This is actually squared, x1 minus x1, 0. And then the next one, you can teach a machine to do this, d squared f dx1 dx2. x1 minus x1, 0, x2 minus x2, 0. The next next one is actually identical, d squared f dx2 dx1. And the fourth one, so you see we went 1, 1, 1, 2, 2, 1, d squared f dx2 dx2, and then x2 minus x2 0 squared x2 minus x2 0. So this kind of thing that, you know, machine just goes 1, 1, 1, 2, 1, 3, 1, 4, gets out to 1n, stops, and it goes 2, 1, 2, 2, 2, 3, 2, 4. It just generates all those terms. Okay. So there's nothing fancy going on there. Obviously, as soon as number of variables is greater than 2, you want to either be doing them in closed form or not at all. Or, you know, you want to just be doing them in index notation or not. I don't want to write out explicitly a whole raft of these things. But yeah, so apparently this matrix of constants here contains the information about maximum or minimum, right? Just like these two contain the information about whether we're at a critical point or not. So yeah, this is just how you mechanically run through these. So I'll just add some stuff about critical points.
Should there have been an x0 vector in the second term?
Probably. I see what you have.
Yeah, I don't have the x0 vector in this term. Should there have been? Oh, yeah, I see what you mean. Yeah, there should have been an x naught in the argument there. Yeah. He was asking about whether, you know, I didn't write those arguments. So the evaluation of the second derivative is at that point, of course, is very important. Yeah. Okay, be that as it may, can't do everything at once. Let's just talk about critical points. So the first thing we have, you know, for n equals 1, we have f prime of x0 equals 0. And then, you know, we can go on with our evaluation. For n greater than 1, we have to have df dxi at x0 equals 0 for I equals 1 to n. So all n of them have to vanish for it to be a critical point. And then if it is a critical point, local, so next would be the question of local extrema. Question of local extrema. And then again, the way we learned this the first time around, n equals 1, we said f double prime of x naught is greater than 0, then it's a local min. And if f double prime of x0 is less than 0, it's a local max. And what if f double prime of x0 is equal to 0? Then it was indefinite, it was a saddle. Right? It could be a saddle. So how do we do the same thing with a matrix? Right? There are a lot more possibilities in a matrix to determine the nature of the local extrema. So for n greater than 1 here, it's a property of the matrix. I'm just going to write this down. And we'll leave it at that for today. We can't do this all at once. So continuing this thought, so for n greater than 1, we need this matrix Fij is positive definite explain these things next time. And if negative Fij is positive definite, then X naught is a local min. Well, positive definite, I just gave us a new definition. So this is a property of a matrix being positive definite. It has to do with its determinants. Okay, so but what it really means, actually we can end with this. And remember, this Fij was evaluated at x0, right, those constants. Positive definite means that for any combination of these delta x's, it's always positive. Right? For any non-vanishing combination of delta x's, it's always positive. Okay? And you can imagine, if it's an n by n matrix, there's a lot going on there, you can't just see it. But generally, though, you're just repeating these criteria in the higher dimensions. So in physical applications, we often already know that this matrix is positive definite just by construction. It came from something that we knew was positive already. It came from the kinetic, potential, what have you. And so we generally don't have to do these tests. This is something out of linear algebra, the determinants and stuff. But anyway, what we'll do next time is a little more practice with this. Okay. So we don't have to learn it all at once, but when you're thinking about it, just always make sure you know that n equals 1 case. So this is the one you really have to know, and then this one just follows it. That's what it is. Good, that's all we've got for today.